For a little background on the lab itself, it demonstrates the principle that objects can gain or lose negative charge by rubbing, pulling, or touching. The loss of a negative charge results in a positive charge. Charged ions or electrons can be transferred from one object to another by the previous mentioned methods. The lab states the total excess charge on an average piece of tape ranges from 1.69 times 10 to the negative 19 to 1 times 10 to the positive 5, which is a very large range. Because of this large variable range, the objective of the lab was to determine the amount of excess charge on the tape within a factor of 10. Materials required for this lab were 1 roll of clear tape, 1 ruler, and 2 thick books. The methods of the lab can be broken into creating the base tape, preparing the U-tape, assessing attraction and repulsion of their charge tape, and balancing gravitational and electric forces. The base tape was created by cutting tape into 8-inch long pieces and creating a handle by folding one end of the strip. The U-tape was created by firmly and smoothly sticking another piece of tape on top of the base tape, then quickly in one fluid motion pulling the top tape off the bottom, leaving the base tape on the flat surface. To assess if the U-tape is attractive or repulsive, I hung the U-tape off the edge of the flat surface and brought my hand closer to the tape to observe any movement. This part of the lab is to observe the possibility of balancing gravitational and electric forces. To do so, I placed 2 books standing vertical and placed the base tape on either end of the books, but to make sure there was a U-shaped lag in the middle. Then, I moved the charged tape closer to the base tape to observe an upward movement of the base tape. If the lagging part of the tape began to float, that meant the electric force upward was counteracting the gravitational force downwards. The first attempt of moving my hand towards the charged tape resulted in no movement, which could have been for a variety of reasons, such as not pulling the tape quickly enough off the bottom tape, the humidity of the room, or not fully flattening the top tape onto the bottom tape. To fix this error, I tried pulling the top tape more vigorously the second time, and this proved to be successful because the hanging strip wavered towards my hand. The tape moved towards a negatively charged balloon, leading to the conclusion that the tape was positively charged. Prior to making my calculations, I had to make some assumptions. Each piece of tape had the same magnitude net charge, and that I had to treat the charge as a single point charge located at the center of the tape. The following equations and key concepts were used in my calculations. The electric force of point B is equal to the charge of B multiplied by the electric field of A, also calculated by the constant multiplied by the charge squared divided by the distance squared, and the electric field of A is the constant multiplied by the charge of A divided by the distance squared. Although there were many questions throughout the lab, because of time constraints, I will present questions which address major concepts. The length of one piece of tape was 0.35 meters. The mass calculated by 1 gram per meter divided by 1,000. The distance measured of floating between the 2 pieces of tape was measured to be 0.051 meters. With these values, I could calculate the magnitude of gravitational force on the floating piece of tape, which was calculated as the mass multiplied by 9.8 meters per second, equaling 0.0057 newtons. Now, because of what we tested earlier of the balancing between gravitational and electric forces, we know that since the top piece of tape began to float, the electric force must be equal in magnitude but opposite in direction to the gravitational force. Therefore, the magnitude of the electric force on the floating tape was also 0.0057 newtons, but in the opposite direction. The methods for Lab 1 and 2 are nearly identical, only differing in the computational model. Lab 1 treated the electric force as a simple point charge, but now in Lab 2, the electric field is treated as a line charge and must be calculated differently. To calculate the charge as a line charge, the tape must be broken into small sections of delta L and delta Q, which represent sections, and then summed to find the total charge. This was done via the computational model using iterations. For my iteration's initial charge, I used the charge obtained from Lab 1's computational model. By testing various charges through iterations, I was finally able to find a charge with the equation of a line charge equaling the force of gravity. To check our computational model, we can look at the balance of forces of the lab, where the force of gravity must equal the electric force in order for the tape to float above the other piece of tape. Now to answer the provided questions. If we had treated the tape as a single point charge like how we did in Lab 1, our values would be significantly different as when we treated like a line charge, because the line charge model calculates the tape in incremental segments as opposed to just one charge with one length. length. By summing the small parts, each with their own distinct values, we are able to achieve a more accurate answer. Thanks for listening, and let me know if you have any questions.